We're now going to discuss the multivariate normal distribution. The multivariate normal distribution is a very important distribution in finance. It crops up in many different applications, including, for example, mean variance analysis and asset allocation, as well as geometric Brownian motion and the Black-Scholes formula. So we say an n-dimensional vector x is multivariate normal with mean vector mu and covariance matrix sigma if the PDF of x is given to us by this quantity here. Okay, so the PDF is equal to 1 over 2 pi to the power of n over 2 times the determinant of the covariance matrix raised to the power of a half times the exponential of this quantity up here. And we write that x is multivariate normal mu sigma. The little subscript n here denotes the dimensionality of the vector x. The standard multivariate normal has mean vector mu equal to 0 and variance covariance matrix equal to the n by n identity matrix. And in this case, the xi's are independent. We can actually see that because in this case, we can write the joint PDF of x as being equal to the product I equals 1 to n, 1 over root 2 pi e to the minus a half xi squared. And that follows just from this line here because mu equals 0. So this term disappears, and sigma is just the identity. So in fact, you just end up with a sum of xi squared divided by 2. So as we saw in an earlier module on multivariate distributions, if the joint PDF factorizes into a product of marginal PDFs, then the random variables are independent. Okay. The moment generating function of x is given to us by this quantity here. So phi subscript x of s, it's actually a function of s. Okay, this vector s, and it's the expected value of e to the s transpose x. Okay, and this is equal to e to the s transpose mu plus a half s transpose sigma s. Now, you're probably familiar with this in the one-dimensional case, so we'll just recover it here. Suppose x is really just a scalar random variable, then the moment generating function of x is equal to the expected value of e to the sx, and it's equal to e to the s mu plus a half sigma squared s squared. And this is the case where x is normal with mean mu and variance sigma squared. So this is the moment generating function of a scalar normal random variable. This is its generalization to a multivariate normal random vector x. Okay. So recall our partition we saw in an earlier module. We can break x into two blocks of vectors x1 and x2 as such. We can extend this notation naturally, so we can write mu equals mu1, mu2, and sigma equals to this sigma 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. And they're the mean vector and covariance matrix of x1, x2. So we have the following results on the marginal and conditional distributions of x. The marginal distribution of a multivariate normal random variable is itself normal. In particular, the marginal distribution of xi is multivariate normal with mean vector mu I and variance covariance matrix sigma ii. So for example, x1 is multivariate normal. In fact, it's got k components, mu1 sigma 1, 1. And similarly, x2 is multivariate normal, mu2 sigma 2, 2. And this has n minus k components. And we have here an example of the bivariate normal density function where the correlation between x1 and x2 is 80%. If we rotate this surface, you can see the correlation of 80% because you can see that large values of x1 are associated with large values of x2. Likewise, small values of x1 are associated with small values of x2. So we can also talk about the conditional distribution. Assuming sigma is positive definite, the conditional distribution of a multivariate normal distribution is also multivariate normal. In particular, x2, given that x1 equals little x1 is multivariate normal with mean vector mu 2.1 and variance covariance matrix sigma 2.1, where mu 2.1 is given to us by this expression here, and sigma 2.1 is given to us by this expression here. And we can get some intuition for this result by just imagining the following situation. So we've got x1 down here, we have x2 over here, and imagine we plot some points from x1 and x2. If you like, we generate x1 and x2 from some distribution, from the bivariate normal distribution in particular. So the mean of x1 is, let's say, mu1, the mean of x2 is mu2. Okay. Now, what if I tell you that we observe that x1 was equal to this little value x1? Well, if that's the case, then you can come up here and you'll see that x2 is more likely than not to be in this region I've circled in red here. So in fact, you would expect the conditional mean of x2, given x1 equals little x1, to be maybe somewhere around here. And this would be mu 2.1. Okay. Likewise, you can see just from this, again, that the variance of x2 will have shrunk, because knowing something about x1 will give us information about x2, and that will decrease our uncertainty about the location of x2. And in fact, this expression here tells us how to actually do this mathematically. So they're conditional distributions. The conditional distribution of a multivariate normal is, again, multivariate normal. We also mentioned that a linear combination ax plus a of a multivariate normal random variable x is normally distributed with mean a times the expected value of x plus little a and covariance matrix a times covariance of x times a transpose.